Assalamualaikum everyone. We are from AS120 SEM 4 group number 1, which is group lab number 3, and today we will present our topic electron microscopy in geology and earth science. Without further delay, let's begin with the introduction. My name is Muhammad Hasanir and I will present my part. Electron microscopy is an advanced imaging technique that uses a beam of electrons instead of light to produce highly detailed images. Compared to a traditional light microscope, it provides much higher magnification and better resolution. Because of this, scientists can observe materials from the nanoscale to the atomic scale. In geology and earth science, electron microscopy is widely used to study mineral, rock, crystal structure, pore networks, and rock texture. Overall, this technology helps researchers better understand earth materials, geological process, and the evolution of rock microstructure. Next, I will explain the significance. Rocks and earth materials contain microscopic structure that preserve important information about their geological history. This tiny feature cannot be clearly seen using a normal light microscope. Scanning electron microscopy, or SEM, produce high-resolution image by detecting signals generated when electrons interact with the sample. This allows researchers to study particle shape, texture, surface feature, and mineral morphology in great detail. As a result, electron microscopy helps scientists identify minerals, understand geological process, and explain the unique properties of different earth materials. Without this technology, many microscopic features would remain difficult to observe. After that, I will explain the first type of electron microscope, which is the scanning electron microscope, or SEM. SEM is mainly used to examine the surface of a specimen. It provides detailed information about surface topography, crystalline structure, and chemical composition. One major advantage of SEM is its very high magnification, reaching up to 1 million times, allowing researchers to observe pictures at the nanometer scales. SEM also has a large depth of field, which keeps more of the sample surface in focus at the same time. Therefore, it is widely used to study the external surface and morphology of rocks, minerals, and other geological samples. My last part is I will explain the second type of electron microscope, the transmission electron microscope, or TEM. Unlike SEM, TEM allows electrons to pass through a very thin specimen. This enables scientists to observe the internal structure of the sample instead of only the surface. TEM can achieve magnification of up to 50 million times, making it one of the most powerful microscopes available. It provides detailed information about the morphology, internal composition, and chemical structure of materials, either qualitatively and quantitatively. Because of its extremely high resolution, TEM is widely used to study crystal structure and defect at the atomic level.
Moving on to key signal and detector attachment, we decide this by the type of microscope used. For scanning electron microscope, or SEM, we utilize backscatter electron imaging to determine compositional information based on atomic weight and energy dispersive spectrum to identify and quantify elemental composition. For transmission electron microscope, or TEM, we use bright field imaging to reveal bulk information through sample thickness, and annular dark field imaging to gather structural and atomic details. Now, let's look closer at EBSD technology, which stands for electron backscatter distraction. This is a macroscopical characterization technique integrated directly within an SEM. It allows us to analyze vital crystallographic information such as crystal orientation, grain boundaries, and phase distribution. Ultimately, EBSD enables research to study how microstructure evolve during deformating, giving us data that conventional optical microscope simply cannot capture. How does EBSD actually work? The mechanism involves directing a focused beam of electron onto a polished tilted crystalline sample inside the SEM. When these electrons interact with the crystal lattice, they scatter and emerge from the surface, producing distinct differentiate patterns known as Kikuchi patterns. These patterns are captured by an EBSD detector and analyzed using software to map out crystal orientation and grain boundaries in high detail. Let's shift our focus to real-world implementation as V-attachable SEM is an incredible powerful tool because it uses electron rather than light to produce highly detailed, high-resolution image of material. This capability allows scientists and engineers to observe intricate structure and chemical composition at microscopic scale that are completely invisible under ordinary light microscopes. We see this put to work across major industry. In mineral exploration and mining, SEM allow geologists to examine rock sample in great detail to identify valuable minerals like gold or copper, which minimize excavative waste. Similarly, in the oil and gas sector, SEM is applied to study reservoir rock, analyze pore space, and determine permeability. This data help locate profitable deposit, improve drilling efficiency, and reduce overall operation costs.
Now, let's look at the real-world application of electron microscopy. First, in fossil and ancient life studies, scanning electron microscopy or SEM helps scientists examine microfossil and ancient microorganisms in great detail. This allows researchers to reconstruct ancient environment and better understand the evolution of life on Earth. Secondly, SEM is widely used in environmental pollution analysis. It can identify tiny particles such as microplastic, heavy metal, and industrial contaminants. By analyzing their size and composition, scientists can monitor pollution sources and support environmental protection efforts. Electron microscopy offers several important advantages. First, it provides high-resolution image, allow researchers to observe very fine surface detail that cannot be seen with optical microscope. Second, it can operate under different environmental conditions, make it suitable for a wide range of research. Third, it is ideal for studying delicate biological and geological samples while minimizing damage. Lastly, it helps preserve the natural condition of hydrated specimen, allow scientists to study sample more accurately and obtain reliable research results. Despite its advantage, electron microscopy also has several limitations. First, sample preparation can be destructive because geological samples often need to be cut, polished, or coated before observation. Second, many samples must be completely dry, since moisture can affect image quality inside the vacuum chamber. Third, SEM instruments are expensive and require specialized laboratory facilities. Finally, SEM mainly produces two-dimensional image, which not fully represent the true dimensional structure of the sample.
Next, let's look ahead at where electron microscopy is heading as we try to push the boundaries of what we can see. We face serious limits in speed, sample damage, and manual data processing. To solve this, we are seeing four major breakthroughs that are completely changing the game. It is for the imaging, compressed EBSD, deep learning in SEM, and AI automation. Let's break down exactly how these innovations are moving the field forward. First up is 4D imaging, specifically through a technique called 4D STEM. Normally conventional STEM only records a single flat 2D image. 4D STEM, however, captures a full diffraction pattern at every single scan point. Thanks to faster detectors, modern EM systems can now collect terabytes of data in a single run. This gives us a massive stream of real-time video containing both spatial and temporal or time-related information. It allows researchers to map out and study the precise atomic arrangements of materials in a way we never could before. Second, let's talk about compressed EBSD technology. Traditionally, mapping crystal orientations take a long time and exposes the sample to a heavy dose of electrons, which can easily damage delicate materials. Compressed EBSD solves this by only scanning selected propositions. It then uses a smart math method called beta process vector analysis to paint in and reconstruct the missing data. Because we take fewer measurements, the scanning process is incredibly fast, and the sample takes far less beam damage. Best of all, it achieves this high-quality imaging without requiring any expensive hardware upgrades. Finally, we have AI automation. Traditional microscopy relies on rigid, fixed spectral libraries which often struggle with complex, overlapping mineral signals. AI changes this by instantly recognizing those overlapping signatures and tracking tiny trace elements with incredibly accuracy. A perfect example of this in action is Distiller, which is a web-based platform that links microscope detectors directly to a supercomputer. Instead of a human manually sitting and interpreting data for hours, Distiller automatically processes the incoming images and runs the scientific analysis in the background. It completely removes the bottleneck of manual data analysis, letting researchers focus entirely on the results. Finally, we have AI automation. Traditional microscopy relies on rigid, fixed spectral libraries which often struggle with complex, overlapping mineral signals. AI changes this by instantly recognizing those overlapping signatures and tracking tiny trace elements with incredibly accuracy. A perfect example of this in action is Distiller, which is a web-based platform that links microscope detectors directly to a supercomputer. Instead of a human manually sitting and interpreting data for hours, Distiller automatically processes the incoming images and runs the scientific analysis in the background. It completely removes the bottleneck of manual data analysis, letting researchers focus entirely on the results.
In conclusion, electron microscopy is an essential tool to geology and many other scientific fields. It provides detailed images that are impossible to obtain using conventional optical microscope, helping researchers make more accurate observations and discoveries. Although it has some limitations such as high cost and complex sample preparation, its advantages greatly outweigh these challenges. With continuous advancement in technology, including artificial intelligence and improved imaging systems, electron microscopy is expected to become more powerful and play an even greater role in future scientific research. That's all from us. Thank you.